The retarded potential, scalar potential and vector potential 两种这个位能。I want to go through this one more time for the harmonic field. So let's assume that at the source, well, the time at the source and at the field location are different. 你注意到，在这个电荷存在的地方，或者是电流存在的地方，这时间不太一样。Okay, this is a time you measure the electric potential. Okay, this is a time you measure your vector potential. 这是不同时间的。Okay, so right at the source, suppose that you have something like a harmonic oscillator, cosine omega t. Sometimes you can just put an initial phase to your source, right? So at your source, you have some charge oscillating like this, and then you want to find the corresponding expression for your potential at a location R. You want to find this expression. Well, but from this expression, you know that the electric potential at R has to follow this form. 你必须符合这个样子。所以呢，你在这里你会放进什么？ Your VRT at this location is going to has this form rho t minus square root mu epsilon r, and integrate over your source divided by r. Okay, but your source oscillate with a frequency of omega. So this means that you have to convert this into omega t minus square root mu epsilon r. So that you can have this argument inside this function. 了解吗？因为你在这里的这个 source 呢，你一定要是这么一个 propagation form. 所以 if you have an oscillation right here, then you have to put omega outside this parenthesis. Therefore, you end up having a term that is rho omega t minus omega square root mu epsilon r. Okay, but you know that your rho, your charge, has this form, so you can continue to convert this into rho not cosine omega t minus omega square root mu epsilon r plus initial phase, and then integrate over your source volume. Okay, 所以一步一步是这么来的。And you know that if you have a harmonic field to start with, if you have a harmonic oscillation to start with, you know that your field, your potential is going to be also a harmonic function. So we can express this with a phasor form. So this you can continue to convert it into a real part of 4 pi epsilon naught 1, and then you have 1 over r rho naught exponential minus j omega square root mu epsilon r plus j phi 0 and the whole thing multiplied with exponential j omega t. And then let me move this up so that on the right hand side you can see it. And then integrate over your source. Okay, and on the left hand side you can also write into V some sort of phasor multiply with j omega t and take a real part of it. Okay, and then you take out this real part and take out this exponential j omega t. Okay, so you end up having an expression that is only related to the phasors. You have phasor function of r equal to 4 pi epsilon naught. Okay, 1 over 4 pi epsilon naught. And then integration of rho naught exponential j phi 0. And then exponential minus j square root mu epsilon r. And then divided by r. And then integrate over your source. Okay, and you recognize that this, you have an omega here. You recognize that the omega square root mu epsilon is equal to omega over u is equal to k is equal to 2 pi over your wavelength. Okay, so now you can convert this into V. Well, before we do that, this is a complex amplitude of your charge. Okay, so you have V equal to 1 over 4 pi epsilon naught, and then exponential rho. You can define rho bar as rho naught is a complex amplitude of the charge, j phi 0, multiplied with exponential minus j k r, and over r dr or dv prime. Okay, this is how you convert the retarded potential, the expression of the retarded potential, to an expression, a phasor expression of the retarded potential for harmonic field, for harmonic sources. OK， 所以呢，这里你可以看到这一项的来源是这么来的。这样了解吗？ And you can do the same thing to this vector potential, OK。所以在下一页你可以看到，就是I did not go through it step by step, but you can see this similar expressions, OK。再下来呢，要跟你介绍的东西都在第一章里头，所以今天 we're going to go through this a little bit fast because this is basically the review for the material you learn in chapter 1. 在第一章底下介绍的大概第一章都有介绍过，所以呢，我们很快的这个复习一下。Any question about this? No? Okay. The expression for the retarded potentials has very explicit physical meaning, has very specific physical meanings. OK， 那尤其是这里头呢，这里产生的 source 产生的这个讯号呢，需要一段时间才会跑到你的 detection point， 这个观念你一定要弄清楚。OK。Now, in the source-free region, suppose that you have a source somewhere here, but you want to know the electric field and magnetic field somewhere far away from the source. Then you can, in fact, derive the governing equation for the electric field and magnetic field. Okay, so let's let's try to establish this equation. Well, at the point far away from your source, either it's a charge or current. There's no charge or current at this location, so we can just safely cross out the source term from the Maxwell equations, and therefore curl of E is equal to minus partial derivative B with respect to time. This is the Faraday's induction law, but on the right hand side of this Ampere's law, you don't have current, and on the right hand side of this Gaussian formula, you don't have any charge. Okay, therefore you start from this 4 equations to establish the relationship between the electric field and magnetic field. Okay, so you put the curl operator to the left hand side of your Faraday's law of induction. So you have double curl on the left hand side. On the right hand side, you have curl of H. And because you have an expression for curl of H right here, so just put this into this side you have curl of H here, so just put this into this curl of H. OK， 所以在这里呢，你会得到一连串的这个式子来描述电场跟磁场。Well, perhaps you want me to go through this for you, so let's do this. You have curl of E. Now, just use Faraday's law of induction. Just use Faraday's law of induction. So you pick up this equation. Okay. So you have minus mu, and then partial derivative of curl of H. But you also know that the curl of H is equal to, from the Ampere's law, you have partial derivative d with respect to t. So put this into this expression. But on the left-hand side, now you must know the way to simplify this from the definition of vector Laplacian, right? On the left-hand side, you have gradient of divergence of E minus the vector Laplacian of E. This is definition of vector Laplacian. On the right-hand side, you get mu epsilon, and then 2 times derivative of electric field over time. By substituting this expression into this. Okay. But from Gauss' law, you know that the divergence of E is equal to 0 in the source-free region. You don't have any source. So you cross out this term. So quickly you establish an equation for the electric field in the free space. Okay, and this is the equation you are familiar with from chapter 1. This is a wave equation. Okay, so this equation has a solution with a form of t minus r square root mu epsilon. You have this kind of solution. So this means that if you have electromagnetic wave, if you have electric field change with time, this is a function of time. So if you have electric field change with time, the field is going to propagate. So when you get this equation, you have to think about physically what happened. 你如果有随时间变化的场在空间里头的话，这个场会跑，这就是电磁波了。Okay, well, you go through the same calculation. You go through the same calculation for magnetic field. Okay, if you go through the same calculation for magnetic field, you also get this wave equation for magnetic field. So this means that if you have a time-varying magnetic field, this field is going to propagate in space. 它会跑多快? Well, from this term, you know that the speed of this wave is going to be this. OK， 因为它的这个解是这个样子，然后呢，你如果看它一个等相位面的话，把它设成一个 constant。Then dr dt is going to be 1 over square root mu epsilon. And we talk about this in chapter 1. Right? 所以现在 we are making a circle back. However you learn in chapter 1 is sort of redisplay right here. 所以越学越简单了，有没有？好。Now, we also talk about Helmholtz equation in chapter 1. The Helmholtz equation is associated with a harmonic field. So again, if you express your E field or H field as a form, say E naught cosine omega t minus omega. Okay, let me go to the original form. T minus r square root mu epsilon plus some initial phase. Okay, if you can express the electric field into harmonic form, same thing if you have H0 cosine omega t minus r square root mu epsilon plus phi naught prime, then you can continue to write this expression to cosine omega t minus kz plus some sort of initial phase. So you can express your EH as a real part of some sort of amplitude in front of it. Say, let me just pick up electric field as an example. E naught exponential j phi naught and exponential jk, sorry, this is r in this expression, jkr, and multiply with exponential j omega t. Okay, this is a harmonic field. And this part of it is called the phasor. That is only a function of r. Okay, so this is a phasor. We call this phasor. Okay, so given this, you put it into the mass equation. Whenever you have a time derivative, to the field, you drop down j omega. Therefore, you convert the real mass equation into a phasor mass equations like this. This is the derivative of the B field with respect to time, and therefore you drop down this j omega when you convert this expression into a phasor expression. Okay, the same thing, you have a Ampere's law, that is that you have a displacement current on the right hand side. So you have the time derivative of d, that gives you a j omega right here. Okay, then follow the same calculation for a double curl operator and so on. Just follow the same steps. You can establish this Helmholtz equation. And this is something you learn in chapter 1. Okay, so we are coming back to chapter 1. Very nice, right? At the end of the semester, we are coming back to chapter 1, and this is something you learn about. And then you do the same thing. You have Helmholtz equation for the magnetic field intensity. Okay, and again, the solution is going to assume this form if it's propagating in z direction. Okay, your solution is going to have this form. exponential minus j kz plus some initial phase。所以这是 harmonic field。有没有问题？这些东西都是第一章的东西。好，我们来看一下这个loss tangent。loss tangent 这个东西呢，你在第一章的时候也学过了。So today is very easy for you. The material basically is in chapter 1. Well, suppose that the field propagates inside some material, and the material is conducting. Okay, so this Ga has to be in this Ampere's law. But you also know that the Ga is equal to sigma multiplied with E from Ohm's law in ohmic material. 在这个 ohmic material 里头呢 ，Ga is equal to sigma E. Well, in chapter 1, we talk about epsilon equal to epsilon prime minus Ga epsilon double prime. If this is a complex number, 在第一章的时候我们说 if epsilon is a complex number, then you're going to have a solution that is exponential minus j kz minus alpha z. And so this means that your field is going to has this form that give you some sort of E naught cosine omega t minus kz plus some sort of initial phase. And then the whole thing multiplied with exponential minus alpha z. Right? You still remember this. If epsilon permittivity is a complex number, then you're going to have a plane wave solution of this kind. And if you plot this over z, initially you have large amplitude and then gradually it taper down due to this attenuation. So the imaginary part of permittivity means attenuation of the wave when they propagate inside this material. Now, specifically, if you have a wave propagating inside ohmic material, then your current is going to have this form. Okay. Now we put this into this curl of edge. So you have two terms. You sum them together to get a complex permittivity. Okay, with this specific form. 所以呢，这个虚数部分可以从哪里来？可以从波在导体里头跑，产生了这个电荷移动，然后碰撞造成的这个能量损失，让它有这个 attenuation 的效果出现。OK， 所以呢，所以呢，你把这个 k 写成 square root of mu epsilon c multiplied with omega, then you have real part and imaginary part. Same as the expression in chapter 1. 你有实数部分、虚数部分。那这个虚数部分呢，你如果把这个 k 放到这里头来的话，你会产生两项。这个虚数部分的 exponential minus kiz basically is written as an exponential minus alpha z right here. Okay. 所以呢，这个波会被衰减掉。那这衰减多严重呢？你可以看到 well, the whole reason you have this imaginary ki, the imaginary part of kc is because the imaginary part of epsilon. 所以这里有多大呢？代表说它衰减的多快。So you can define a loss tangent. Usually this is a small epsilon double prime is small compared with epsilon prime. OK， 那所以呢，你可以把它定义成一个角度，这个 loss tangent 是 epsilon double prime over epsilon prime, and for a conductor you have this expression. OK， 那这个 loss tangent 越大，代表说它的衰减越快，因为它的这个分子的部分是它的这个 complex permittivity 的虚数部分。Okay, so loss tangent basically just sort of an index telling you how fast this wave is going to attenuate. Okay, 有没有问题？那因为通常这个 epsilon, usually this epsilon double prime is much less than epsilon prime. So basically, you have this small angle roughly equal to epsilon double prime over epsilon prime. Usually this is much less than 1. Okay, 通常这个值是远小于1。因为你不会喜欢你的做一个电磁波，辛辛苦苦产生一个能量呢，把它打到会很快会被吸收的东西里头去。OK， any question？ 没有问题 ，right？ 没有问题的话呢，我们要开始介绍平面波、平面电磁波。那这个很多也是在当初第1章里头有介绍到。平面波 in this course, we deal with a harmonic field. We deal with harmonic waves. 随时间变化的这个 sinusoidal wave 叫做 harmonic wave. So we start from the Helmholtz equation. And this is something you are familiar with from chapter 1 again. 从第1章你就了解到的。Right? 那这个呢 harmonic 这个有好几种解。In different coordinate system, you have different solutions for the Helmholtz equation. And the simplest solution is called plane wave. When we talk about plane wave, it means that the wavefront is a plane. Okay, 我们来看一下。Suppose that we do not know the solution and just guess it. 猜它。Let's guess that there's a solution like this. Well, but this is not the only solution. Okay, I have to point out that this is the particular solution in the XYZ coordinate system. But just assume that you have such a solution, and then put this into Helmholtz equation. After you do the vector Laplacian, and then you thought that there's a requirement for your ks, ky, kz. OK， 这个 requirement 的话就是 ks square plus ky square kz plus kz square has to be equal to k square. 所以这个 kx, ky, kz 并不是随便可以设定的。OK， 那我们来看，他告诉我们说，你如果满足这个条件，你这个可以是它的 Helmholtz equation 一个解。那我们看看这个解它的特性是什么。OK， 那now this k dot r you can write into a vector ks, ky, kz along x, y, z directions respectively, and then this r basically just a position. Okay. So to sort of simplify the expression, you don't want to write 3 terms. 你可以把它变成一个这么一个形式 ，OK， 这个形式里头呢 ，k 到 r 这个 k 把它有一个这个 unit vector 在那个地方，因为你知道这个必须要成立 ，OK， 所以呢，你在这里 k 你可以把它写成一个 unit vector。Okay, now that you have this expression, so you can write this unit vector as kx over k over x direction. Okay, plus ky over k over y direction, plus kz over k az direction. ，alright， 所以呢，你可以把它写成一个 unit vector k， 这个 k 的 unit vector， 然后呢，the whole thing exponential minus jk dot r now is sort of exponential minus jk a scalar right here, and then your unit vector multiply with r, and r is just a usual position vector x along x direction plus y along y direction and z along z direction. So now we have mathematical expression. We want to understand what it is. Okay, physically 它是什么东西？那一样，第一章的时候都有介绍过，我们来看一下。This is a complex expression. And the way to convert this into a real expression is to multiply this complex expression with exponential j omega t and take real part of it. This is how you convert a phasor back to the real variable. Okay, so you multiply this with exponential j omega t and take real part of it. You end up having this harmonic field. And by now, you should be very familiar with this process. 你应该非常清楚这个很简单的这个写法 ，right？ 那在这里呢，你注意到就是这个 usually this the compressed amplitude has a magnitude and also a phase. So if you take a square root of if you take an absolute value of it, you usually end up having some constant phase right here. 所以这个样子，我们从一刚开始的时候呢，把它拆我们有这么一个解。然后呢，把它变到这个形式来之后呢，我们要去看看这个解所代表的意义是什么。OK， 这个解所代表意义基本上就是说它是一种波。And then whenever you talk about wave， 你怎么知道有这个波的存在 ？If you just throw a stone into a water pond，把这一个石头丢到水里头去，你看到什么？你看到波往外传，你怎么知道那个波在往外传 ？Because your eye look into a single phase point， 你在看一个这个同等相位面，看到它一环一环的往外传，那个一环一环就是等相位面。Okay， so they set the phase to be a constant.If you set this phase to be a constant and then you take a photo, when you take a photograph, you set t to be a constant. OK， 这所有的这个物理的动作其实都对应到这数学式子里头的变数的设定。OK， when you look into the ring of the wave, basically you are setting the phase to be a constant. When you take a photograph,you are setting t to be a constant value. Okay, so with t a constant value, this means that with a constant phase and also a constant value for t, you are looking into a constant phase. You are looking into a constant value for k dot r. 所以 k dot r 是一个这个你在看那个波的时候呢，在任何一个时间点，你在这个 k dot r 是一个 constant。Okay, so geometrically k dot r equal to constant is a plane like this. 因为 k 这个 r 这个 plane 上头任何一个位置是 r, and k is along some direction. K dot r is a projection of this r onto this axis. It's a constant. Then every point on this every point with k dot r a constant is going to form a plane. 一个面上头的 k dot r 是一个常数，这是你国中、高中时候学过的。Right? So we call this a plane wave. So when we say it's a plane wave, we say the constant phase plane is a plane. When you say that it's a spherical wave, then it means that the constant phase plane is a spherical shape. Okay? 那这个都是在第一章的时候呢有跟各位介绍。好，我们来看一下，这里头我们把它写成一个这个 unit vector 的方向。你知道这个 plane, the direction of this plane is along k direction or along en direction, this unit vector direction. OK， 这 unit vector 的 direction 呢，你这个 kx、ky、kz 跟这个 unit vector 这个方向的关系是什么 ？OK， 我们来看一下，在这里 ，when we say this, let's write this into cosine alpha, write this into cosine beta, write this into cosine gamma, because this is the value less than 1. This is also value less than 1. So you can write into an angle. OK， 那这个代表说是什么？这个 cosine alpha 呢，其实就是呢这个 k 投影到 x 方向上头的角度。Right? So it's very easy to know that your kx in fact is equal to k cosine alpha. So now you geometrically connect those variables. 注意到刚开始的时候呢，这个 kx、ky、kz 怎么来的？是我们假设有个解是这个样子。现在呢，有很清楚的物理意义在里头，它有很清楚的几何意义在里头。这个 alpha 呢，这个 k vector 跟 x 轴的这个夹角就叫 alpha，because kx is a projection of k onto x-axis. Okay, and for beta, this angle is a angle between your k vector and the y-axis. And same thing, gamma angle is the is an angle between k vector and the z-axis, because you have this kind of projection. And so in chapter 1, I told you that the alpha, beta, gamma, cosine alpha, cosine beta, cosine gamma are called direction cosines. OK， 因为它定义的这个 k vector 相对于 x、y、z 坐标的方向。Any question? Quite clear, right? 很清楚。现在几何的这个图像都有了。那 k 的方向的话，就是波的波前跑的方向。为什么？因为从这个式子里头，你知道 k 到 r equal to constant. This k is the direction of this plane. 所以这些很清楚，这个整个几何概念应该非常清楚了。K is the direction of the wavefront. So if you have a spherical wave like this, then your K is going to be perpendicular to your wavefront. 这个叫做 wavefront， 波前，或者是呢，你的波前可能在我们现在介绍里头是这样子往前跑，这个垂直方向 is a direction of k， OK。但相对于 x、y、z 坐标，它的这个角度呢，k 跟 x 的夹角就是 alpha，and the angle between k and y is beta，angle between k and z is gamma，OK。这样整个物理的图像都很清楚了 ，right？ 所以，所以 given a k in the x, y, z coordinate system。假设刚刚这里是 x， 我现在把它写成 x, y, z， 写成这个样子 ，I can do it, right? And then suppose that I have a k vector along this direction, okay? And this k is equal to a magnitude multiplied with a unit vector. And this k for harmonic wave is equal to 2 pi over wavelength. Suppose that this angle is alpha. This angle, well, let me do this. This angle is say 30 degree, and then with y you have 45 degree. With z you have 60 degree, for example. would you be able to write down the plane wave expression for this wave? You can do it, right? Because your AN is equal to cosine 30 degree along x direction plus cosine 45 degree along y direction, and then cosine 60 degree along z direction. This is the direction of this unit vector, the wavefront direction of this wave. So this is easy, right? Ax plus 1 over square root of 2 ay plus 1/2 az. Okay, and your electric field, your phasor field is going to be equal to some initial complex amplitude multiplied with exponential minus j k an dot r. 所以这个部分你可以把它乘开来了。Is equal to E naught exponential minus j k square root of 3 over 2 along x direction, because you know this r is equal to x ax plus y ay plus z az. Okay, so just do a dot product between this an and this and multiply with k. So this is too easy for you, but I go through this for you anyway. Plus k 1/2 az. No, this is z. Now, how would you write down ERT? You basically multiply the whole thing with the exponential j omega t and take real part of this. Okay, 你把它整个乘上 exponential j omega t， 然后呢 take real part of it， 所以这个式子你很快的可以写出来。这个实数的这个式子呢，这个 electric field is going to be equal to some absolute value of it, and then you have cosine omega t minus square root of 3 divided by 2 k along x direction, and then minus 1 square root of 2 k along y direction, and then minus 1/2 k along z direction, and then don't forget you have an initial phase coming from E naught equal to E naught absolute value exponential j phi 0. Okay, so this is your final solution for your plane wave. 所以我这样走一次，就让你知道说，只要你知道这个波跑的方向，你可以把这个平面波写出来。Okay, when I say if you know the direction of the wave, means that it means that your alpha, beta, gamma is well defined. 这个三个角度已经完全定义出来了。Okay, any question? 没有问题right？清清楚楚的。那这个有点都在复习第一章的东西。那这里呢，其实就是刚刚介绍过的。好，这里再来呢，有一点这个向量微积分在里头。那curl of E, if you have a plane wave, then you have this kind of expression. If you do curl of E to this, you end up having basically you end up having this jk minus jk pop out cross with E. Okay, and this is a steps to get this result. You can just read by yourself. Okay, you do care of this, and then you do a differentiation of this this constant, you get nothing. According to this vector identity, this is sort of differentiation by parts. Okay, you first differentiate this f with gradient, and then cross with g, and then you leave this alone here and do curl of g. But for this curl of E, this f is E naught. So this is a for this f is this complex exponential. Okay, for this curl of g is curl of E naught. So this is nothing, becomes 0.它这个10呢，跟这个 x y z 无关，所以你做这么一个动作的时候，右微分变成0了。So you end up having this result. So curl of E equal to this, but you also know that the curl of E from the Faraday's law of induction, on the right hand side you have this. OK， 左边这里等于负 jk cross with E， 右边这里呢是这个样子。哇，这个式子告诉你 E 跟 j 的关系。OK， 所以 if you equate jk cos E equal to minus j omega mu h, you can organize this into h equal to omega mu k an cross with E. OK， 你只把这个移过来，把 k 写成 k multiplied with an. So if you know the solution for E, you know the solution for H. So this is an easy way to calculate the magnetic field from a known electric field. Okay, and this k, you know this k is equal to 2 pi over lambda. Okay, so k over w basically is equal to 1 over u, or equal to square root of u mu epsilon. Okay, so you put this k over w into this expression to get, you have square root mu epsilon divided by mu an cross with E. This is going to give you epsilon over mu an cross with E, and you define this eta is equal to square root mu over epsilon. So you end up having 1 over eta an cross with E, this expression. Okay, and this eta is equal to 377 ohm in vacuum, and it's called intrinsic wave impedance. Again, this is the result you learned about already in chapter 1. 在第1章里头已经学过了。OK， 所以这是一个告诉你说这个如何从 E 来求 H 的方法。但是 in addition, it also tell you the direction relationship between E and H with this cross product. 这个 cross product 告诉你说 H 必须跟这个它跑的方向、波跑的方向跟电场的方向都要垂直。Okay, so in addition to the relationship of the magnitude between E and H, you also get the directional information about E and H. Okay, 那另外一个这个式子是什么呢？是 Ampere's law， 在这个地方。This also will give you the relationship between E and H. OK， 那这个基本上呢，你如果知道 H 的话，你可以从 H 来求出你的 E. But this also offer you the information about the directions, relative directions of the propagation direction, H field and E field. 所以这个式子呢，告诉你一件事情，就是 E 跟这个它波跑的方向跟 H 的方向呢是互相垂直的。OK， 这个告诉你说 H has to be perpendicular to the k direction and e direction。所以从这两个式子，你可以找到，它们之间有个这么一个关系 ，E 跟 H 跟跑的方向必须垂直 ，E 跟 H they have to be perpendicular to each other。Okay, and you also follow the right-hand rule. If you point your four fingers to E and rotate your four fingers along H, then your thumb direction is going to be the propagation direction of the wave. OK， 所以这里头告诉你很多的这个讯息在里头。回去读一下，下次上课是下礼拜3。OK， 那不要忘了这个下礼拜1之前，你要再到电子材料行看一下这些跟磁场相关的电子材料。OK， good。